The electromagnetic spectrum is a spectrum of electromagnetic radiation or energy by wavelength, respectively. If we look here on the left-hand side, we have high energy waves, which are short in wavelength. The distance from top to top is small. Gamma rays are the electromagnetic radiation with the highest energy and the shortest wavelength. All the way to the right, we see long wavelengths, a long distance from top to top or crest to crest, and we have things like our radio waves. These have long wavelengths but are low in energy. If we look here towards the center, we see the visible light portion of the electromagnetic spectrum. We see that violet light is associated with a short wavelength, C 400 nm nanometers, and red light is associated with long waves, C 700 nm or 700 nanometers. This goes in order of the colors in the rainbow. Starting from the right, we have red, orange, yellow, green, blue, and violet light. These go from red, low energy, long wavelength, all the way to violet, high energy, short wavelength. Niels Bohr thought that electrons were found in orbits because each time he looked at hydrogen gas, he was able to see unique bands of light that were associated with very specific wavelengths. When we look at an incandescent bulb that is plugged in and turned on, we see white light. White light is the combination of all light. This would be a smear of red, orange, yellow, green, blue, and violet. There are not specific wavelengths, but when we look at a pure sample of gas, we will actually see very specific wavelengths of light given off. This is a regular incandescent light bulb. When the light bulb is turned on, what we see is white light. But when we look at the light that's given off through a diffraction grating, what we see are the colors of the rainbow: red, orange, yellow, green, blue, and violet, in order from long wavelength to short. This shows us that the white light is actually a combination of all the wavelengths of light. When Niels Bohr excited electrons in a pure sample of hydrogen gas, he looked through diffraction grating and broke that light up using a prism. This prism split the light that was produced into 4 unique wavelengths: red, blue-green, blue-violet, and violet light. Because every time Niels Bohr saw these unique wavelengths of light, he said to himself that electrons must be making very specific transitions, and there is a very specific amount of energy associated with each transition. This allowed him to say that electrons are moving from one set location to another, and the position of the electrons was a fixed distance away from the nucleus in what is called an orbit. This is a hydrogen gas discharge tube. This glass tube is filled with pure hydrogen gas. It is standing in a high voltage electricity power source. When that high voltage electricity is allowed to run through the hydrogen gas, we see this vibrant pink color. When the diffraction grating is used to break up the light, what we see are these very distinct bands of light. There is one with a wavelength associated with red light. There is one associated with blue-green, one associated with blue-violet, and one that is associated with violet light. This is a gas discharge tube that is filled with helium gas. We can see that before the diffraction grating is used to look through the light, we can actually see this pale yellow-white color. This should tell us that this is a combination of almost all the wavelengths of light. When we look through our diffraction grating, we see these vibrant lines of red, yellow, blue, and violet light. Last, we have neon gas in the gas discharge tube. We see this vibrant orange color that is given off from the neon gas before the diffraction grating is used to view the light. We can see with the neon several bands in the red, orange, yellow, and one in the green here. What we notice is each one of these elements is giving off unique bands of light, specific wavelengths created by certain electron transitions. When two like charges, such as positive and positive, get near each other, they repel each other. The same goes for two negative charges. They are like charges, so they repel each other. But opposite charges, such as positive and negative charges, will be attracted to one another. According to Ernest Rutherford, there was a small, massive, dense positive nucleus in the center of the atom, and all around that nucleus were negative electrons. A positive nucleus would attract negative electrons. Niels Bohr also concluded that there would be a positive nucleus in the center of the atom attracting electrons. So for electrons to move away from the nucleus, they must absorb energy. Energy could come into the atom in the form of light, electricity, or heat, and it could hit that electron. That electron could absorb that energy. If the energy is enough to break the attraction from the positive nucleus, then that electron would actually be able to jump to a higher energy level. In this higher energy state, the electron is in what is called the excited state. In this excited state, the electron is very, very, very unstable. So as soon as an opportunity arises, the electron will drop back down to a lower energy level. When the electron is close to the nucleus, it is known to be in the ground state, and the ground state is a more stable state for the electron. Because energy is conserved, as the electron drops back down towards the nucleus, energy is lost in the form of electromagnetic radiation. What we see is that the arrow for a wave is pointing out of the atom, showing that energy is going out. Some of that electromagnetic radiation, remember, is part of the visible portion of the electromagnetic spectrum where we see as different colors of light. So, to review, when the electron is close to the nucleus, it is in the ground state. The negative electron is attracted to the positive nucleus. But if the electron absorbs energy in the form of heat, light, or electricity, the electron can actually jump away from the nucleus. When the electron jumps away from the nucleus, it moves to a higher energy level, where it is in the excited state and is less stable. Because here in the higher energy level, the electron is unstable, it will then drop down to a lower energy level. When the electron drops to a lower energy level, it is termed in the ground state and is much more stable. As the electron drops back down to a lower energy level, energy is released in the form of electromagnetic radiation, or light. As you can see, the wave is pointing out of the atom, showing that that energy is being released. If a lot of energy is absorbed in the form of heat, electricity, or light, the electron has an ability to make a very high jump, in this case from energy level 2 all the way to energy level 6. Now remember, this is an unstable state. The electron is far away from the nucleus, and as a result, it is unstable. So as soon as an opportunity arises, that electron will actually drop back down closer to the nucleus. In the hydrogen atom, when that electron drops back down from the excited state, energy level 6, to the ground state, energy level 2, electromagnetic energy is given off. And this is in the form of violet light. Because different amounts of energy can come into the atom and excite the electron, different transitions can be made. With less energy, the attractive forces can be broken still, but the electron could move from energy level 2 to energy level 5. When the electron goes from the excited state back down to the ground state from energy level 5 to energy level 2 to gain stability, it is going to give off this blue violet light. When less energy is absorbed, but the electron is still able to overcome the attractive force of the nucleus, the electron could move from energy level 2 to energy level 4. Because this is an excited state, as soon as an opportunity arises, that electron will fall back down closer to the nucleus. If the electron falls from energy level 4 to energy level 2 in the hydrogen atom, it is going to release electromagnetic radiation in the form of this blue-green light. If even less energy is absorbed by the electron, it can still overcome the attractive forces of the nucleus, the electron could jump from energy level 2 to energy level 3. Because this is still farther away from the nucleus than the original position, that electron is termed in the excited state. As soon as an opportunity arises, it will drop back down to the ground state and go closer to the nucleus. When it does, because this is a small drop, what we're going to find is we're going to have a less energetic wave that's given off. Red light will be emitted when the electron in the hydrogen atom moves from energy level 3 to energy level 2. To review, in the hydrogen atom, when the electron drops from energy level 6 to energy level 2, electromagnetic radiation is given off in the form of violet light. Violet light is high in energy and has a short wavelength. This makes sense because the transition is very, very big. In the hydrogen atom, when the electron falls from energy level 5 to energy level 2, electromagnetic radiation is given off in the form of blue-violet light. You can see that the wavelength is a little bit longer here, and there's less energy associated with this color of light. That makes sense because the drop is a little bit smaller. In the hydrogen atom, when the electron drops from energy level 4 to energy level 2, electromagnetic radiation is given off in the form of blue-green light. In the hydrogen atom, when the electron falls from energy level 3 to energy level 2, electromagnetic radiation is given off in the form of red light. What we can see here is red light has the longest wavelength and it is associated with the least amount of energy. This makes sense because this is the smallest transition.